Okay, so it seems like we have a few students here, and so let's just get started. So today we are going to talk about heavy metals. Here we have like 6 topics. So first, I will have a brief introduction about what is heavy metal, and then I'm going to talk about the environmental fate of the heavy metals, especially the specific speciation and the cross products. And then we are talking about the effects of heavy metals, and then the source and the related regulatory standards of the heavy metals. And finally, I will briefly talk about the analytical method for the trace metal analysis, because we are going to use this method in the lab. And so first, what is heavy metal? It's here. So the heavy metals refers to the elements with metallic properties, and the density of the heavy metal is usually greater than 5 grams per cubic meter, and the atomic mass is usually greater than 20. So in this definition, we can see that aluminum, which is a toxic metal, but it is not included in heavy metal. Here are some most common toxic heavy metals in the environment. So I also find some pictures of these heavy metals, like we have arsenic, chromium, copper, lead, cadmium, mercury, and zinc. But we know that the pure form of these heavy metals is hardly appear in the environment. Maybe we have some pure copper in the environment, but for others we do not. These heavy metals usually exist in the environment in the forms of the compound. So here I also find some pictures like of different states. Let's just say chromium. We can see that for the chromium, it has different oxidizing states. So it may, like depending on the amount of oxygen that the environment have, it can have different states. And we can also see that with different oxidizing states, they have different colors. This is same for the lead. So anyway, then let's look at the environmental fate of these heavy metals. So first is solubility products. I think we have talked about this in lecture 2B, but here let's just talk this again. So solubility product constants are used to describe saturated solution of ionic compounds of relatively low solubility. And a saturated solution is in a state of dynamic equilibrium between the dissolved, dissociated ionic compounds and the undissolved solids. And the keyword is saturated solution and equilibrium. So basically, if the solution is not saturated, then cross product constant, solubility product constant will not apply. And here is an example. So suppose we have this compound. So M here refers to the metal, and A here refers to the cation. And we can see this is a solid state of precipitation, and it can dissolve in the water, and so it will be dissociated into this form. And in this case, we know that the equilibrium constant of this equation would be the concentration of M, Y plus, and this is X times the concentration of A, this is X minus, and this is Y, and divided by the concentration of this precipitation. But in a water solution, we just focus on the water phase or the aqueous phase. So we just say this one equals to 0 because it is in the solid phase. So this equilibrium constant equation become this one. So, and we can define this product is the solubility product because it is a product of the concentration. And on the right side, it shows the some of the solubility products of different common compound. And we can see this is calcium carbonate. We can see its KSP is like this value. And we can also see this is magnesium carbonate, and the KSP is this value. And based on the KSP, we can see that the KSP of calcium carbonate is smaller than the KSP of magnesium carbonate. In other words, we would expect that the solubility of calcium carbonate should be smaller than the solubility of magnesium carbonate. So basically, it can tell us the relative solubility of different compounds. And we can see that, like in general, like in high school, we may say that these two compounds, they are insoluble, but basically it will have a very small amount of ions that is dissolved in the water. And so for this one, do you guys have any questions? No, okay. And speaking of the ion, we also have a common ion effect. So the common ion effect refers to the decrease in solubility of an ionic precipitation by the addition of the solution, by addition to the solution of a soluble compound with an ion in common with the precipitation. I think this definition is a little bit abstract. So let's just look at an example. Here is the example. So suppose we have this calcium carbonate, and we know that it will dissolve in the water with a very small amount. So in general, it will dissociate into calcium and carbonate ion. In this case, we can see that based on the chemical equilibrium theory, we know that if we increase the concentration of calcium, so if this increase, we know that this chemical reaction will go to this direction. So more calcium carbonate will form. Similarly, if we increase the concentration of this CO3 minus, and we can also see that this also go to this direction. And finally, the concentration of calcium carbonate, like the precipitation, will form. But in reality, we cannot add these ions directly because of the charge balance. So we may add something like calcium chloride, or for this one, we may add like sodium carbonate. So we may add this to the solution, and in this case, the chemical equilibrium will go to this direction. So maybe we only have a relatively small amount of calcium carbonate, but by adding these stuffs to the solution, we will have more precipitation. So basically, we can decrease the solubility of calcium carbonate by adding some other chemicals. So for this one, do you guys have any questions? No? I think the next one is about influence of pH. So the influence of the pH is pretty similar to that. So here are also some like chemical reactions in the solution, and here are the KSP of this corresponding equations. Let's just focus on these three equations, and we can see the first one is like aluminum have some reactions with hydroxide, and this is the chromium with hydroxide, and this is ferron with hydroxide, iron with hydroxide. So in this case, let's just focus on the first one. So in this equation, let's see what happens if we reduce pH. Do you guys think which direction will this equation go? On the right side, or this direction.
So all of the solids will dissolve.
Excuse me?
All of more solids will be dissolved.
Oh yeah, the right side. Oh yeah, Yeah, I was confused about directions. Yes, it will go to this side. So more like AL3 plus, they will form. Because if we reduce pH, in other words, we will have more OH. If we reduce pH, it means we will have less OH minus. And if this is reduced, then we will have go to this direction to compensate the removal of OH minus. And similarly, if we increase pH, then the concentration of aluminum will decrease because it will go to this direction. And this conclusion is similar with these two equations. And by summarize them together, we can see that if the pH is reduced or if the environment is more acidic, we will have more heavy metals in the 2+ or the 3+ form. And we know that because they have the charge, they are not precipitation, they are dissolved. They can dissolve in the water. So basically, as the pH decrease, the heavy metals, they are more movable, like they have ability to move to other places. So for this one, do you guys have any questions? No? Okay. So why do we care about this? So for this part, this is not required in this class, but I just want to add this because I think this can help us to understand what is happening. So basically on the right side, it shows the mechanism of the plant to absorb aluminum and some mechanisms of aluminum to have some damages to the plant. So basically when a plant is absorbing aluminum or some other metals, it will absorb like the ionic form. So basically, only the metals in the ionic form, it can be absorbed by the plant. And when it is absorbed by the plant, we know that it is a toxic metal, although it is not a heavy metal, but it is toxic. So it will have some like different negative effects to the plant. So which is bad. So basically, we do not like the metals in the ionic form, so which is bad. And here are some more detailed reactions of aluminum with the hydroxide. We can see that it may combine 1 hydroxide, 2 hydroxides, 3 hydroxides, and so on. But again, this is not required in this class. We just need to understand the previous slides. So based on this, and we also have its equilibrium constant. And we know that the Kw, like the water, has a constant, like the constant of the product of the concentration of hydroxides and the hydrogen. So basically, we can transform these relations into the relations here. In this case, these are the log concentration of different species, and this is a function of pH. So basically, we can construct the relation between the concentration of the pollutant and the pH. By having these relations, we can make a plot. So basically, this is the log concentration, and this is a pH. And we can see that because they are just linear functions. So basically, we have like different lines, and each line represents different species. But note that this refers to the concentration. We can transform this into the fraction. So basically, this is the percentage. Basically, so this is the fraction, and this is similar to the carbonate system that we have, like something like this, if we remember this. But this just shows the different species of aluminum. We can see that this is a pH and this is percentage. From this plot, we can see that as pH decrease, we will have like more aluminum 3+ in the water solution. And as the pH increase, then we will have this one first, then we will have this one, and finally we will have this one. And we also know that in the natural water, that is around 7. So basically, we will have this form. This is a kind of like the precipitation. So the plant will not uptake this. But if the pH of the soil or the water decrease, become very acidic, then we will have more aluminum 3+, and this is bad for the plant. So basically, we do not want the soil or the environment become very acidic. And similarly, we can also have like this plot of different other heavy metals. Like this one is zinc, this is lead, this is cadmium, and this is copper. And from this plot, we can always see that as the pH decrease, all of the heavy metals will in the form of like the ionic form, so which is movable and they can be uptaken by the plant, so which is bad. Okay, so far, do you guys have any questions? No. And then we are going to talk about the speciation. So basically, depending on the form of the metal is found, either dissolved, precipitated, or attached to the particle, oxidized or reduced. Like they have very different implications for its movability, fate, transport, and toxicity. So basically, like if we have a metal species, it may generally have 3 forms. Like it can be attached to the suspended particles, and it can also form like colloid, and it also can be like truly dissolved. And when it is truly dissolved, it can be the free ions. So basically, this is bad. And it can also have like different oxidizing state. And it can also form like complex. It can form complex with inorganic ligands and organic ligands, like with large or small molecules. And it may have some different isotopes and the organometallic compound. And from this, we can see that, let's just say if it is in the free ions, so it will have charge. When it has charge, it will be very soluble in the water because it is polar. So the water solubility will be very large, and then it will be very easily to be transported with the water. On the other hand, if the metal combined with some organic matters, like maybe it could be like organometallic compounds, or it has some form some complex with the organic matters, then because of the organic matter, it will be relatively non-polar. In other words, the KOW may increase. So the water solubility will decrease, but the KOW will increase, and the KD will also increase. So notice that KD refers to the water and soil partitioning coefficient, and the BAF will also increase. So if the heavy metal become relatively organic, then it will be very bioaccumulative. And here are some examples. So the first one is as in lead. And we have the notes that COL refers to colloid, and MT refers to the metal thioneals. So basically, this is an organic compound. And we can see that when we have some lead from the runoff, like from the mining pond, and then because it is in the ionic form, it can move with the water or runoffs from the rain, and then it may go to the rivers or go to the lakes. When it is go to the river or the lakes, it may form like colloid, and it may also form in the organic form. And once it is in the organic form, it can be uptaken like by the small animals or the plankton in the environment and be uptaken by the fish. And finally, it could be uptaken by the human, which is bad. And because of the bioaccumulation. And similarly, we also have this mercury. So mercury may have like the similar path, like it go to the water, go to the lake, and then it will have its organic form. Like this is methyl mercury, and it will be uptaken by the animals or the organisms in the lake or in the river. And finally, it may get into our foods, which is bad for the human beings. But mercury also has some differences because like the pure states of mercury has relatively large vapor pressure, so it can stay in the air. In other words, it can transport in the atmosphere and go to like other place or remote places, and then it will precipitate and form some other stuff. So far, do you guys have any questions?
Question two, where you have the general.
This one?
What is the difference between the dissolved ones that are formed complexes with an organic ligand versus the organometallic compound?
Yeah, I think that this is a good question. I think the differences is that I think when it has the organometallic compounds, this is relatively, I would say, relatively unstable, or it may combine with some other larger organic matters. But on the other hand, when it has the ligand, like EDTA, we know that it is very stable. So I would say this could be very toxic because it may release the lead when we uptake it. But for this one, because it can form very stable complex, so the toxicity is relatively low. So any more questions? Yeah, like because I also have heard like if someone has a heavy metal, like if they drink or eat the heavy metals in a large amount, then you may just drink some EDTA to form the complex to decrease the toxicity.
Seems like they form different bonds between the two parts.
Yeah. Oh yeah. Yeah, they may form different chemical bonds.
Yeah.
Then let's look at the environmental effects of the heavy metals. Why do we care about that? So the first one is in the soil because of the heavy metals. And we know that it can combine with water to form like the precipitation. So it will also form hydrogen. So the pH will decrease. It will lead to the problem of soil acidification. And it may also reduce the nutrient availability in the soil. For example, we know that sulfur is important, or the phosphor. But when we have some metals or heavy metals, it may form precipitation with these nutrient elements, which makes them become unavailable to the plant, which is bad. It may also inhibit the soil microbial activity. So on the right side, it is a summary of the adverse effects or the mechanism of the heavy metal toxicity to the soil microbes. So I'm not going to read them, but we can see that it has like a variety of different negative effects to the microorganisms in the soil. And the next one is to the plants or the crop production. So basically, it may reduce the seed germination, reduce the plant growth, reduce the plant weight, and decrease of the photosynthesis. And it may also accumulate in the edible parts. So when we eat the contaminated plant, that is bad. And again, on the right side, it shows some of the adverse effects or the mechanisms of the heavy metal to the plants. Again, I'm not going to read this, but if you are interested, you may just take a look. And we know that Maria is also doing some research on the heavy metals to the plant growth. So I took this picture when she was here doing the growth chamber experiments. So basically she has different types of plants. We can say this is green beans and there are some different food and this is peanuts. And then she adds, I think, the lead to like the lead of different concentrations to each plate. And then she is monitoring the growth and the mass of different plants. I'm not sure if she has the results yet, but she's doing this types of experiment. And the next one is about the heavy metals to the water and the groundwater. So the most common metal pollution in the freshwater comes from the mining companies, especially the acid mine drainage system. And the metals remain in the sediments for a long time. And because they are non-biodegradable. On the other hand, they form the sediments because they have alkalinity in the environment. So the pH of the water may stay relatively high because of the alkalinity. And finally, they will form precipitations in these water bodies. And with the low pH, metals are in the ionic form, and they are more movable and more toxic. So basically, alkalinity is important to protect from move or the toxicity of these heavy metals. And metals can enter the food chain through invertebrates and fish. And another way of water pollution is like the leaded pipes, which is an experiment that we were doing. And the next one is a heavy metal in the air. And due to most industrial activities like the power plants or the waste installations and mining, and it can have like the transboundary air pollution, especially of lead, mercury, and the cadmium, can affect most of the remote regions because when we are burning like the stuffs, then these heavy metals will be released in the atmosphere at very high distance, and then it will be transported by the winds a very remote distance. And the heavy metals in air can deposit over plants, soil, and water, entering the food chain through the plants and fish, so which is bad. And heavy metals can also be inhaled by humans, like when it is in the atmosphere. And also when we have like some particles in the atmosphere, and these heavy metals, they may just attach on the surface of this particle. And when they inhale the particles, then these heavy metals will be released in our body. And the next one is about the heavy metals to our health. Here are just some facts. So cadmium exposed associated with the kidney and the bone damage and lung cancer. Lead exposure have developmental and neurobehavioral effects on features, infants, and children, and elevate blood pressure in adults. And we also have like some adverse effects of the mercury. On the right side, here are some summaries of the negative effects of different heavy metals, and we also have some permeable levels. So again, I'm not going to read this, but if you are interested, you can take a look at this. So far, do you guys have any questions? No? The next one is about source of the heavy metals. It can be classified as two. So the first one is natural source. So basically, we have two main natural sources, which is the weathering of soil and rocks, and also the volcanic eruption. But for the anthropogenic sources, like we have like different types. Like it may come from smelters, waste installations, and power plants. It may also come from the wastewater sludge from the wastewater treatment plants, and also the fertilizers and pesticides or livestock manure, exhaust gas, and urban runoff. It may also come from the deterioration of the sewage pipes, and of course the mining. And on the right side, I just find the paper that is talking about the urban runoff, like the heavy metals in the urban runoff. It's just so like this table, like the comparison with other studies of HM. HM here refers to the heavy metal from RDS, and RDS here refers to the road deposited sediments. So they are just the sediments on the side of the road. And we can see that like the urban runoff may contain like these different types of the heavy metals. And the next one is about regulatory. Oh, so we are also interested about the regulatory standards of the heavy metal, like in different environmental components. And the first one is in agricultural soil. And here I add agriculture because like if we are interested in the soil, we have this one. It doesn't open. So if we are doing the ecological risk assessment, like we have this table that we have already seen it. And in this one, we can also see that we have aluminum, but we also have some other different types of the heavy metals. So if we are doing the ecological risk assessment, we may use this as the regulatory standard. But they are not the agricultural soils. For the agricultural soil, I find this table. So this is the regulatory standards of heavy metals in agricultural soil of different countries. We can see that different country has different standards. But interestingly, we can find another fact that, for example, UK and the US, we can see that for this arsenic, the standards are very different. Like we have about 400 for difference. And this is also same for cadmium and the mercury. So when I was looking at this, I just had a question. I don't know the answer, but I'm just interested. Like, do you think why different country has different standards? Do you guys have any ideas? Yes.
Maybe like because like it's so high, everybody just have to kind of do.
Oh, yeah, I think like because the UK is a traditional industrial country, so they may have relatively high amount of pollutants on average. So yeah, I think that works. Do you guys have any?
I think the enforcement is also important. It's like, I know it's high in Germany, let's say 50 for arsenic, but it's probably worth 500 for us, yeah. But then it's actually enforced very heavily versus, you know, yours might be case by case. Maybe they find it, maybe they won't find it. You're good until they don't find it. Whereas there's a little, I guess, the regulations, because like if there is a level where they have to go find people for their actions, then it also has to be in a level where you find it frequently enough.
Yeah, yeah, I think.
Or like not so frequent, but basically they want to stop everyone from doing everything they want to do.
Yeah, and I also find one possible answer that could be maybe so. Like for example, maybe in some country we focus on apples, and for other country maybe they focus on the rice. But for the apple and rice, they may have different absorption rates of different heavy metals. So maybe this may not be true, but maybe for the UK, they grow the plants that has a relatively low uptake of arsenic. But in United States, we may have the plants that is highly bioaccumulative of arsenic. So that's why we have different regulations. but I'm not sure the true answer, but okay. So the next one is about the regulation in natural water. So notice that this is a natural water, that's the drinking water. And this is adopted from US EPA federal registration. So this is a regulation in United States. And we can also see that we have different allowable concentrations in the natural water, especially the mercury concentration is pretty low. In other words, I would say the mercury is very toxic or very bioaccumulated. And the next one is in the drinking water. Yes, for the drinking water, and we can see like we have the WHO and we also have US EPA standards. And here we have the P and S, and we can see that P refers to the primary, which refers to health-related effects, and S refers to the cosmetic or arsenic effect. So basically, if we are drinking, we are interested in the primary concentration. And we can see, again, we have like different standards of these heavy metals. And so the last topic is about how to measure the heavy metals or the metals in the environment. In this class, we are going to use ICP. Also, in general, in general, we have different methods for separation and extraction. Like we have the chromatography methods, capillary electrophoresis, and ion chromatography, liquid extraction, and ionic change or cold precipitation. Actually, I haven't used these techniques in my experiments, and we may also have some measuring techniques, like we have atomic spectroscopy, and we also have inductively coupled plasma optical emission spectrometry, ICP ODS. So I think in our lab or in the lab in next week, we are going to use this device to do the measurement. So the basic theory is that we can pump our sample into this torch, and then if you use some magnetical methods to heat up our sample, then we will have this flame, and this flame has a very high temperature, because under the very high temperature, the atom of our sample will be activated, and then it will emit electromagnetic wave to the environment, and then we can receive this electromagnetic wave. So basically they are lights, but they may not be the visible lights. And then for each light, we may have like different peaks, and then we can just differentiate different peaks, so we can know which elements we have. I think after next week's experiment, when we have more understandings of this instrument, and we may also have like the narrow activation analysis, X-ray, photoelectron spectrometry, and like electroanalytical methods. And again, for me, I only use this method before, and for other methods, I haven't used them. And for this one, do you guys have any questions? Okay, so I think this is the end of the class. So you guys can take a look at this. And here I want to mention that I think the time may be a little bit limited, so I just extend the deadline of assignments 6A and 6B to April 18. So the original was April 14. So I just add the weekend. So if on Monday, but the quiz 8 and quiz 9, they are not changed. So the deadline of quiz 8 and quiz 9 is April 14. So that will be the next Thursday. And in this Thursday, we will not have class on this Thursday, but you may need to watch this video on YouTube. And I also post the link in the on Canvas. And this lecture is about the flint, some background or some theories. And finally, I want to talk about the quiz.